Hello, this is my lab report for Physics Lab 1, measuring constant velocity. And so the purpose of this is to compare and contrast measured versus simulated motion and describe the position and change of velocity at constant velocity. I will be using Tracker to measure the position and change of velocity of the marker and in the observed data. And I will be using Excel for all of my data managing and graphing. And then I'll be using GlowScript to code the physics simulation. The most important equation that I'll be working with is R final equals R initial plus V times delta T, and that is the position update formula. This allows us to measure or predict where an object would be given constant velocity, or if we're assuming non-constant force, it would be V final. Constant force is V average. However, we're assuming that this is net force equals 0. So the main takeaways is that the observed motion will differ from simulated because Fnet is not equal to 0, and position update formula will help us out in finding the average velocity and the velocity that we need to encode. And then we'll be looking at constant velocity and zero acceleration graphs and and it should look like a straight line and a constant slope on the position over time graphs. So as we're looking at it, ideally our position versus time graph is like the one below, where it's just a straight line, and velocity does not change in the velocity versus time graph. It is a constant. So some of our assumptions is that net force equals 0, and that the system is the marker. The marker will roll perfectly straight, and that there's zero friction between the marker and the table, and that the table is not in a slope, and that there are no other forces acting on it, ideally. So the system is the marker, and the surroundings, the table, the air, hand pushing the marker, gravity, and any other unknown forces that could be in this. Ideal conditions, and the initial conditions is that in the observed experiment that the hand will give an impulse to the marker is the system and will roll across the whiteboard, and friction is assumed to be negligible. In the simulated, the ball is the system, net force equals 0, and those surroundings are encoded into the simulation. The observed experiment a hand will push the marker to set it in motion, and we'll take a video from above to observe the path, and using Tracker software, track the position of the marker over time and determine average velocity and graph its position. In the simulated, we'll code a ball to move at a constant velocity and take the average velocity from the marker for this and measure displacement. So the coding setup is where we encode a ball, and we give it a position vector, a velocity vector, and delta T is going to be the amount of time in between frames, just so the data lines up when we're graphing it. And as it goes through, we'll use position update formula time after time to update the position of the ball. Fnet equals 0, so the velocity of the ball does not change at all. And by finding the correct velocity, this is taken from the tracker data, and the axis we can see from the slope that negative 0.3951 is going to be meters per second, and the velocity of the marker. So the simulation of the ball, here's our ball in the green. It starts at the yellow and moves along the green path, and this is the two graphs that we got out of it for position versus time and velocity over time. Observed motion, here's the video of it.
That wasn't too bad. That wasn't too bad.
Well, try that one more time.
That wasn't too bad.
That's better. So we can tell that the marker moved at a constant velocity, or we can assume that the marker moves at a constant velocity and it rolled across the table. That is the video that we worked with in Tracker. So in collecting data, we use the tip of the marker as the point that stayed constant, and we set the axis to the path that the marker rolled across, and we used a ruler to calibrate Tracker. What if the axes were different? Well, since we're only looking at the x-axis data and using that to calculate the v-average, it would be smaller if it were on a tilt, and it'd basically be the sine of the difference between the angle of the difference between the two axes that has changed compared to what it is now. This is aligned with the actual path, and so v is only in the x direction, and it's going to be the biggest in this position. If you were to flip it and say flip the video upside down, then the marker would be moving in the positive direction. Here, velocity is negative because it's moving in the negative direction. How do we know how many forces are acting on the marker? Well, there's friction, gravity, hand, air resistance, other known forces, other particles flying from space. We don't know how many forces are acting on the marker. And so there is discrepancies we can tell, but they look very similar, but they're different between observed and simulated motion position. Conclusions, because we will never know how many forces are actually acting on the we would never know how many forces are acting on the observed, and so we can never create an ideal environment, and there will always be a discrepancy between simulated versus measured data. Thank you.